In the last video, we made a simple circuit to interpret a stream of data from a floppy disk drive. The first stage of the circuit was for clock recovery to synchronize with the serial data stream from the disk drive, and the second stage was splitting the FM encoded data stream into clock and data bits. I hooked the whole thing up to an Arduino for testing, and had the Arduino try to read some data from the disk, and it kind of worked, but it wasn't very reliable. I think it was right on the edge of the timing that the Arduino could manage. And my main conclusion was that I need to put a bit more into the circuit itself to reduce the load on the CPU or Arduino or whatever it is I hook up to it. So that's what I'm going to do in this video. I'm going to extend the circuit to try to make it separate the data into discrete bytes so that the CPU only needs to read from the circuit once per byte coming from the disk rather than once per bit coming from the disk. Now remember what the FM data stream looks like. We have interleaved clock and data bits, so a byte consists of 16 bits in this data stream, 8 clock bits and 8 data bits. So this is going to reduce the kind of load on the CPU by almost a factor of 16. We'll go from having to read data once every 4 microseconds to about once every 64 microseconds. So one of the challenges with splitting this serial stream of bits into bytes is that we need to know where the boundaries are between the bytes. We could just count off 16 bits at a time, that is 8 clock bits and the corresponding 8 data bits, but we need to actually start on the byte boundary, otherwise the data we're going to get out is all going to be rotated and shifted and it's just going to be weird. So you can think of a track on a floppy disk as kind of a blank canvas onto which is painted a number of data regions. And those data regions come in two main types. One of them is an ID chunk and the other one is a data chunk. And the idea is just that each data chunk is preceded by an ID chunk which gives some context for what that data is. So the ID chunk consists of what's called an address mark at the start, which is a data byte of FE with a clock byte of C7. And after that address mark, the ID chunk simply contains the track number, the head number, the sector number, and a size code which says how much data is going to be stored in this sector, followed by a CRC that's just used to make sure that there were no read errors when reading that data. And that's the entire content of the ID chunk. It's quite a small thing. And what happens is 17 bytes along the disk later, the drive should find the start of a data chunk. And the data chunk is again preceded by an address mark, but in this case the address mark has a clock of C7 and a data byte of F8. And that address mark is then followed simply by the raw data bytes that the user wanted to store in the sector. So if it's a 256 byte sector, that address mark is followed by 256 bytes of data. After the data, another 16-bit CRC is stored, just to check that the data was correctly stored and received, and that's the end of the data chunk. And a track on the disk generally consists of an alternating sequence of ID chunks and data chunks like this for however many sectors there are. Another factor I haven't mentioned here yet is that the address marks are always preceded by writing 6 bytes of zeros. And I believe these zeros are there to make sure that the reading circuit can get properly in sync with the data stream before it needs to read an address mark. In my Arduino program, what I was already doing in order to kind of solve this problem of trying to find the byte boundaries within the bit stream was simply looking for the address marks. So I was looking for any situation where what I thought was the clock was set to C7 and what I thought was the data was set to FE. And if I ever found that, I assumed that I'd found an address mark for an ID chunk and I continued to read the data from the ID chunk. And all my program was doing was just sort of dumping out what that data was, and so giving a list of all the sectors on the track on the disk. So on the Arduino, it's fairly easy to do a full 16-bit comparison of the 8 bits of the clock byte and the 8 bits of the data byte with C7 and FE, for example. I don't really want to do that in an electronic circuit because every bit I compare costs me real estate on the breadboard. So what I'm going to do is use an alternate mechanism that I've thought of, which will reduce the amount of bits I actually need to compare, while still retaining enough confidence that what I've found is actually a valid address mark. I'm going to make a circuit which just looks for those 3 missing clock bits and 1 of the missing data bits of the preceding 0 bytes. And that should be enough for me to fairly confidently identify the starts of these address marks. Note that the region in green is the address mark byte and the region in yellow is the preceding zeros, and I've indicated at the bottom which data will be in the shift register at the time that we make the comparison. So note that we haven't actually read the entire address mark by the time we make this decision that we are currently reading an address mark, and that means we need to read a few more bits into the shift register before we tell the CPU or Arduino that it's time to read a byte. But once that's done, we'll know we're in sync with the data stream, and after that we just need to alert the CPU once every 16 clocks to read another byte. And because all these bits are being compared against 0, it's actually really easy for me to take these 4 bits out of the shift registers and just pass them through a NOR gate. So if any of these bits is set, then I know that we're not currently triggering this kind of address mark detector circuit, but if all the bits are 0, then the output of the OR gate will go low, and we can use that to trigger the rest of the circuit. So that's the plan. Let's see how well it works. So here's the circuit from the last video. Let's disconnect the scope and the Arduino and then start putting the new components in. So here are the shift registers, the 595s, and I think I decided I want to take clock bits 0, 1 and 2 and data bit 5, which was probably somewhere over here. And these are the pins I want to check for zeros on in order to start triggering my byte synchronization circuit. So I don't actually have a 4 input OR gate. Instead of doing that, what I'm going to do is I'm just going to run them all through diodes and use a resistor to pull down the signal. I'll put the resistor at the top. Let's put it a little distance away from that one. So by doing this, the resistor will normally pull the signal low, but if any one of the 4 pins that I'm sampling here happens to be high at the time, then it will pull the signal high. It doesn't matter if multiple pins are high at the same time, and the diodes will prevent them from shorting into each other as well. I'm going to spread these diodes out quite a bit. So these are all pointing with the black band towards the top, and the top goes through that resistor to ground. So there's my 4 diodes and a pull down resistor, sorry. And I want clock pin 0. Clock signal 0 is actually the second pin of this shift register over here. So that's the first one I'm going to take. I'll put that down there so that you can see that. And then I want clock pin 1. And remember, the data and clock are interspersed here, so clock pin 1 is the next along missing one. And that will go in here as well, into the next diode. And then I think it was clock 2 next. So this is essentially 3 clock bits in a row, and this comes from the 3 zeros in the C7 data. Sorry, the C7 clock byte has 3 zeros in a row in it, and that's kind of what I'm filtering for here. And the other one I want to pull from the data byte, and it's going to be bit 5. So bits 0, 1, 2, and 3 are on this shift register for the data byte, and then bit 4 is here. So bit 5 will be the 3rd pin of this shift register. So there we go, we have clock bits 0, 1 and 2 and data bit 5 are going through the diodes into this pull down resistor, so that if any of those is high, then the signal at the junction here will get pulled high. And really what I want to do next is just look at that on an oscilloscope, because the key thing here is making sure that that is happening at the right time during the revolution of the disc. So let's get the scope hooked up again to that. I'm going to bring the Arduino back just to power things up, because that's how I've got that configured at the moment. So the disk drive is mostly still hooked up here. I haven't got it spinning at the moment. The read data line's all there, so that's all fine. It will be driving this circuit. I'm just going to step a few tracks just to get it off track 0, because track 0 is a bit corrupted on this disk. And was there anything else I need? The index hole I unplugged. I'm not going to worry about that. I don't need that. So yeah, I think we're good. Oh, the only other thing is I want the shift registers to always be clocking at the same time that they're shifting. So I'm just going to join the two clocks of the shift registers together here. And I can remove that pull-up resistor now. I'm not going to need that again. So now the shift registers are always clocking their output storage register at the same time that the shift register shifts, and I think that means it'll actually be 1 clock cycle behind, but that's not a big deal for us. So what do I want to put on the scope? I'm definitely going to want to see the signal coming off the floppy disk drive, so I'll put that on channel 1. I could put my clock signal in here, but I don't think... Yeah, let's put my clock signal in as well, just to see how this all lines up with that. And other than that, the main thing I want to probe is this new signal that I've just added there. So let's measure the voltage across this resistor. And I'm going to start the disc spinning. So there's that on the scope. What do we need to do? We're currently triggering on the data. So I'm going to change the trigger to the new signal. It's down there. Okay, so this is interesting. So there's some noise on the signal there. Let's just reset this. There's actually this little spike here is causing the scope to trigger. So I'm going to have to watch out for that. That's a problem with my my diode OR gate. I think what might be happening there is that some of the bits are transitioning during the shift, and it's actually pulling it down a little bit too far there during that stage. Anyway, if I've lowered the trigger threshold on the scope, and that seems to be working fairly well like that. So if I zoom out a bit now, what I'm hoping to see, if I take a single frame snapshot here, is I'm hoping to see one of those address mark bytes. So let's have a look at the yellow trace now. Going to zoom in again. And remember that the kind of sequence that gets stored on the disk is a very long sequence of zeros, which we have over here, followed by a byte with the clock pattern of C7, so the clock bits are starting for this one, so we've got a 1, a 1, a 0, 0, 0, 1, 1, 1, so that's correct, that's C7, and the data byte is probably either FE or FB, depending on whether this is a sector ID or actual user data. So what have you got? 1, 1, 1, 1 is F, 1, 1, 1, 0 is E. So this was a sector ID byte, and that should mean that the signal coming low here, our little notch that we've created, should be enough for us to now trigger a counter. From this point on, we can then trigger some kind of latching to the CPU side of things once every 16 clock ticks after that point. So that's pretty good. I think that's going to be really good, because that reduces the frequency at which the CPU needs to poll things by a factor of 16, which is pretty nice. I'm going to do another capture and just see whether we get a different data byte. That looks the same. Let's get another. Same again. I mean, it's good news that it's the same. At least it's being consistent. Although by now it's being a little bit too consistent. Oh, there we go. So if you check the traces now, this is the clock bits. Again, we've got 1, 1, 0, 0, so that's C. And then we've got 0, 1, 1, 1, so that's 7. And for the data bits, we've now got 1, 1, 1, 1, so that's F, and 1, 0, 1, 1, so that's B. And FB is the address mark for a data block on the disk. So I think this is working really well. Every time I do a single shot capture here, we do seem to get the right sequence of bits there. Oh, having said that, this one shouldn't have come up. I wonder why that got tagged. So the problem here is that this looks like it's just a long run of zeros. It doesn't look like we had any missing clock bits here at all. So let's have a closer look at why that might have happened. I don't have the data off the side of the scope, unfortunately. So this is where we triggered. And when we trigger, we expect there to be a clock pulse of 0, which I guess is this one. I'll have to double check whether the trigger arrow is right next to the 0 clock pulse. or whether maybe that was the one it would be triggering on. But we're expecting to have a 0 here, then I'm not checking the data bit there, then a 0, and then a 0, and then quite a bit further over here there should be another 0 in the data. I think it was data bit 5 I was on, wasn't it? So if this is data bit 0, then that's 1, 2, 3, 4, 5. So this one got missed. So that's the second one in the capture. Let's zoom in and have a closer look at that, because there might be a phase problem with my my 250 kilohertz clock here. Okay, so that's the first pulse. Actually, I mean, my clock is rising really early there. I think that's just about missing the edge of that pulse. Interesting. And over here it got a 0, and again here. I think the reason that this triggered my capture was that this clock pulse in blue here was too early compared to the actual data from the disk. What I've got in yellow here is actually the inverted data from the disk, and something I didn't mention much in the last video was that in order to get the Arduino to run stably, I actually had to invert the read data from the disk twice before feeding it into my clock synchronization circuit, and that was really to delay the clock slightly to avoid exactly this kind of problem. What I really want to do is delay it even more, and I could feed it through a couple more NOT gates. It's not ideal. Another way of delaying it more would be to add a D flip-flop and use the D flip-flop to delay the signal. That's a fairly standard way of doing it. So I've tried out a couple of ways now to delay my clock slightly so that it doesn't rise too quickly after the data line changes state from the floppy disk drive. Now, the first thing I did, because I didn't want to completely redo the whole circuit, the first thing I did was just use more of the inverters, chain more of them together to try and get a bit of delay from that. That didn't seem to be sufficient, so I bit the bullet and I have actually rearranged the circuit a bit. I've tidied a few things up, as you can see, clipped some diode leads and so on so they're nice and short. Now I moved the shift registers along and I've inserted a D flip-flop, a dual D flip-flop. That's a 74 AHCT 74 I think. And I'm using the top half of it as D flip-flop to delay the clock that's coming out of this counter chip here. So it's delaying the output from this counter until the next tick from the 4 MHz oscillator, which is maybe a more consistent and a bit more substantial way of delaying than simply chucking a load more inverters in. So you can see with the changes that I've made to the circuit there, this is now working really well. I've got my little notch down here. There's a slight curve to the falling edge of this now because I stuck a little capacitor in, and that was to get rid of some of the glitches that I was seeing on the rest of the line there. So it kind of smooths that signal out a bit. That's only there for the oscilloscope to be able to trigger on it reliably, so I'm not going to leave that in the circuit when I have say the Arduino hooked up. Anyway, you can see at the top now, I mean, this is the reconstructed clock signal, this is the data signal from the drive, inverted, so up means 1 now and down means 0, and you can see the standard pattern of 1 1 0 0 for C in the clock, and then 0 1 1 1 is 7, so that's C7 in the clock line, and in the data line we've got 1 1 1 1, then we have 1, and either 1 1 0 or 0 1 1, you'll see from time to time, and those are FE and FB in the data part of the signal, and FE indicates that the upcoming block is a sector ID chunk which contains the track, head, sector, the length code and a CRC, while FB indicates that what's about to follow is sector data for whichever sector had the previous ID chunk. And FB would then be followed by just a whole bunch of actual data bytes on the disk, and a CRC at the end as well. So what I'm going to do next, if I just disconnect the Arduino power from the board, what I'm going to do next, as I said towards the start of the video, is I'm going to extend this to consistently advertise to the CPU or the Arduino or whatever is connected every time it thinks a byte has been received on the shift registers. And the way I'm going to do that is simply by using the address mark detection there to start a counter. So this is another 74ACT163 or something like that. Same counter I used before. Again, it's salvaged from my VGA sprite circuit. The VGA sprite circuit is not dead. It's very easy to put these back again later. So I'm going to put this counter in, and what this counter is going to do, initially it's going to count 6 of my reconstructed clock pulses, because that should take us from the point at which the address mark detector gets triggered to the very end of the address mark. So remember that the address mark trigger is based on a point that's, I think it's like 6 bits through the byte rather than 8 bits through the byte. So there's a few more bits to pull, and I think it's 6 clock ticks is what we're going to need to wait for from my earlier calculations in order to allow the shift registers to accept those extra bits. And then the shift registers should contain the full clock and ID of the address mark. And after that happens, the terminal count signal on this counter will go high for 1 pulse, for one reconstructed clock tick. And that's something that the CPU will be able to notice, either through an interrupt or just by polling for it. And when that happens, the CPU can read that data. At the same time, this counter is a 4-bit counter, so it's going to reset and count for another 16 ticks. And after another 16 pulses on the reconstructed clock, the terminal count's going to go high again, and that's exactly the right number for the next byte of data to be received. So once the address mark has triggered this, it can just keep running forever, counting 16 ticks at a time, and every 16 ticks it will tell the CPU that there's a new byte of data to read. So the general hookup of this counter is exactly like the one we did before. So that's most of the signals hooked up there. The main ones missing are the parallel enable, which needs to come from our brand new address mark detector. Like that. And then the only other thing to hook up here is I think it's pin 15, is the carry from the counter, and that's what we're going to use to tell the Arduino when it should take some data. So I'll get that hooked up to the Arduino, and I'll update the code, and I'll run it, and I'll see whether we get a more consistent sector dump this time. So here's the Arduino all hooked up to the circuit. One mistake I made earlier on that was particularly significant was the initialization value for this this counter over here, which I had set to 6. Now the reason I set it to 6 was because I wanted to skip 6 bits before telling the Arduino that the byte was ready when it was reading an address mark. However, what I overlooked was this is an up counter, not a down counter. So if I wanted to give a signal after 6 bits, I need to set it to 16 minus 6, which is 10, which is what it's set to now, rather than 6. So yeah, I've corrected that here. That's the only real change from the other circuit that you already saw. The Arduino is hooked up to the terminal count output from this counter on pin 15 there, and that's taking the place of what was the clock before in the Arduino code. So that goes high once per byte and triggers the Arduino to actually read the data from the shift registers. The white wire is still connected to the index signal from the disk drive so that it can tell when the index hole passes, and the green wire here is not really doing anything anymore. It's not actually connected at that end. So that's the hookup for the Arduino. The disk drive hookup's of course exactly the same as before, and the hope here was just that it would be more reliable. So let's turn on the disk drive and see that running. So over here we have the serial monitor as before, showing the output from the Arduino program. And what this program does is the same sector dump as before. In fact, it's almost the same code. The main change I made in the code was making it not wait for all 16 ticks of the bit clock before reading any data. It actually only waits for a single tick of the byte clock instead. So that's the main change to the code that does that sector dump there, and you can see that that's working absolutely fine. The additional piece of code I added is this thing which verifies the actual data chunks of the sectors. So as I said before, the track, head sector and size codes are all stored in the ID chunks on the disk, and that's what the sector dump was reading. This verified sector data section is actually reading the data for each sector, and it's checking the CRC to make sure it read all the data correctly. And as you can see, that's working very stably now. I'm not seeing any errors at all here now. So yeah, I'm really pleased with that. Those changes to the circuit have really helped. This is the new function for actually reading a sector of data off the disk, and you can see that it takes the sector number as a parameter, and then the len is the number of bytes in the sector, and then we have this array of bytes which the data gets stored in. So the first thing we do is wait for the address mark of an ID chunk, and then we read the track, head and sector out of it, and if the sector matches the sector we're looking for, then we break out of this while loop and continue with the function. If it doesn't match, then it's just the wrong sector, so we loop around and look at the next one. And if we hit the index hole, then this function will actually return false, and we'll go through the second half of the if here. And we just decrement this index counter, and that just means, as it says in the comment here, that if we see the index hole twice, then we assume that we're not going to find this sector, that it's not actually present on this track. After finding the right ID block, we just look for the next data block after that ID block, which is done by waiting for the address mark F8 instead of FE. And assuming we find that without hitting the index hole, all we do then is we read the right number of bytes out of it, and store those in the array that was provided. So we store all the data, and then we also read the CRC that comes at the end of the block. Again, we just check we didn't hit the index hole or read invalid data there. And then I've got the CRC calculation here using a CRC library I found for Arduino, just to verify it's correct. And the output that we were seeing earlier on was saying OK for all the sectors, and that means that they did actually read all the data and read the correct CRC. So that's wonderful. So I'm really happy with how that circuit's working now. One thing that I haven't done yet here, that will make life even easier for the Arduino, is latching the actual bytes coming from the shift registers when that clock pulse goes positive there. The reason that would be a good thing to do is that currently the Arduino is only notified once every 64 microseconds by that byte signal. But it still has to read the shift registers really quickly before they've moved another bit. So there's still a kind of a timing constraint there that I'd like to get rid of. And simply putting some D flip-flop latches after the shift registers, which are triggered by the byte signal here, would probably do the trick for that. Another option might be to plug the data byte of the shift register into a 6522, and then you can connect the clock signal here into one of the control inputs on the 6522, and for port A the 6522 can actually latch the incoming data when the control changes state in the correct direction. So that could be used as well for a sort of really lightweight way of latching this stuff, especially if it was being used in a 6502 computer. So that's probably the kind of thing I'll do next. But yeah, I've been really pleased with how this has gone this time round. I think the fact it can read arbitrary data off the disk, it's reading the actual data from the sectors, is wonderful. And it seems very reliable at it at the moment. So yeah, really pleased with that. Hope you guys have enjoyed this. As always, let me know in the comments what you think, if there's anything in particular you're interested in more information on. And do the old like, subscribe and notifications if you want to be notified when there are new videos.